back to bionics of surfaces. So, thermodynamics at the moment. I'm having difficulty tracking the camera, but never mind. We will persevere. There we go. Try and not pull it off my desk. So today we were thinking about, or we wanted to think about, liquids boiling. We had freezing last time. Freezing is interesting because we can undershoot the freezing point, but it's not so interesting because water, for example, almost always freezes at 0 degrees. It's quite hard to make it change. But what about boiling? So if we look first of all, thermodynamics, which is what we were doing with our water. So we were considering initially thermodynamics, and we were saying at equilibrium, which is when nothing happens, which would be with water. At boiling point, when it's boiling and condensing, falling back into our chamber. So that's what I'm trying to draw here. We're at equilibrium, so the water's evaporating and it's also condensing. That means delta G is equal to 0. It gives free energy of our liquid and our gas are the same. It's not changing, and therefore we've got some features in here. Therefore, naught is equal to delta H minus T delta S, and we can rearrange we can rearrange our equation to give us T. T is equal to delta H divided by delta S, which seems quite reasonable, except that we have a problem. The problem is that the temperature of boiling is not fixed, and also if we close a container full of water, or not full of water, but with some water in, it will achieve equilibrium at whatever temperature we have at it. So there are conditions where we have an equilibrium, whatever we do, and that means that there isn't a single temperature where this happens. What I like to do at this point, or somewhere near this point, with this subject is to go on and on about another subject, about the idea of having different models for the same thing. So let us step across to this other picture here for a little bit. This is a picture which also is a model for boiling. The model is slightly different. What I was saying there is, if we take a bubble, this is the bubble, oops, it's a bit difficult to do because it looks weird because I sort of reach out of one side and my hand comes in the other side, but there it is. There's our bubble, and if we think about when will that bubble get bigger, so what I'm interested in is when will this bubble get bigger and then it will grow out of control. So if I change the temperature, the pressure inside the bubble should change, and when I get to a certain temperature, the pressure inside the bubble will be some kind of threshold value where it will grow, and that temperature will be the temperature of the atmosphere plus the temperature of the depth of the pressure of the atmosphere, P at, and the pressure of the depth inside the water. Which means if we have very, very deep water, then we will have a different pressure. We'll have a different pressure that we have to reach. So we would expect our boiling point to be different. If we do that, we see that, so that if we want the P of the bubble, to be is greater than or equal to P at, I can't write this way out, P at, oh, P is rubbish. If that's what we're expecting for boiling point, we might have missed a few things. So let's go back to the ice. When we remember that as the ice formed, that's better, it made a new surface. And now we have a new surface that's curved, and it's causing us a new problem. And we can think about whether this curved surface here is helping the bubble to grow or stopping it. You can see if it's got surface tension, and the surface tension is pulling inwards like a balloon, it will increase the pressure inside the bubble slightly. What we can do is look at how that is affected by the shape. Oops. So we can see that when the bubble's really, really big, then we're just pulling on a straight line, and that's not affecting the pressure on one side or the pressure on the outside. So this is in and this is out, but they're the same because it's flat. If we make it into a very tight curve, then we're pulling into the bubble, and it's being pulled in from all sides, so we're going to increase the pressure inside. So we would expect the bubble pressure to go up and up and up as it gets smaller and smaller and smaller, and that reveals pretty much the same problem that we had with the freezing. That to make a very, very tiny bubble needs a bit of extra force. Once it's going, or if we have some sharp edges inside here, or if we have something that will start bubbles forming, we will be able to keep going as long as we like. So I've added the surface tension term onto here, but we can still see that the pressure of the bubble is going to have to be equal to the atmospheric pressure plus an extra bit. And if we change atmospheric pressure, we would expect the boiling point, which is when this inequation suddenly comes true, we would expect the boiling point to be different. So if we increase the pressure, we would expect the boiling point to be higher, would be harder to reach. And if we decrease the pressure, we would expect it to be easier to reach. And we can do an experiment to show that. I'll do that next time I do a video when I go back into the lab. All we need to do is close a container and change the pressure in it, and we can see whether we can change the temperature at which something boils. I tend to not use water because it's easier to get something like ethanol to boil. But we'll see what happens this time. I've actually got a job that I need to do, so maybe I'll use something other than water that I'm trying to distill anyway. So if we change the pressure in here, we would expect the boiling point to change. This agrees with possibly some of our experiences. If you go high up enough in altitude, so if you go to Tibet or somewhere or Chile, where it's comparatively high, for humans anyway, the atmospheric pressure is lower and the boiling point of water goes down. It doesn't go down hugely, it's only a little bit, but apparently it's difficult to cook. If you're on the top of mountains, particularly in Tibet, it becomes difficult to cook in the same way that you would cook near to sea level, because the boiling point of water is lower, and then the maximum temperature that you can reach with something that's wet goes down, and so you have a lower temperature for cooking if you're boiling. Obviously, if you have a pressure cooker, then you can get out of that problem. But if you are heating it up to boil, then it will be cooled by the water boiling off it, and it will always stay somewhere around boiling point. And that will cause problems, possibly, in both directions, if we make it the pressure too high or it goes too low. What does that say about this other side? The other side is also a model of the world. It's an engineering model of the world that says the water is a continuum, it's stuff, and the gas is a continuum, it's stuff, and we can say, we can make equations that are true. So they both show the same thing, which means that we must be able to make, or for this equation to be useful, it has to also change boiling point with pressure. And that means that it's inside one of these two terms. Okay, so I'm just trying to, I've gone back a little bit and I've checked on what I should have been saying, which isn't entirely true. So let's just make a statement about the entropy. The entropy is a function of both temperature and pressure. So we can make a function of temperature and pressure that will tell us the change in entropy. What we're interested in here is the change in pressure, but there is a smaller change of entropy with temperature, which means that Gibbs free energy diagram is only limited value. Gibbs free energy equation is only of a limited value because we have to take into account the change in entropy with temperature. But let's do that first. So why is there a change of entropy with pressure? And what is the entropy anyway? So we can introduce that. At least we'll have to come back to it anyway, because I know it's difficult to get your head around it, and I'm probably not doing it very well because I am rusty. So here we are. We've got some molecules in here, and the question is, what happens to the entropy, which was some form of randomness, but it's not a simple form of randomness, so we need to think about that a little bit more. The standard school definition of untidiness is a little bit unhelpful in this case because it's not quite that. So what we have here is some molecules, and they can be or atoms, and they're moving around in a box. And if we change the pressure, we would effectively be changing the volume that they can move around in. And that means we have reduced the possibilities for those molecules. So if we change the pressure, we can assume that the entropy, particularly of a gas, will change. And that will also tell us why the change from water to liquid wasn't having very much effect. We can measure a pressure or a temperature of 0 degrees centigrade with ice melting in different places, and it doesn't change very much, whereas the temperature of water boiling does. And that's because the volume of a gas changes way more than the volume of a liquid or a solid when we change the pressure. And if we're changing state particularly, so we're boiling, we're changing from a liquid, which doesn't change volume very much, to a gas that does, it's going to be much more effective than if we're changing from a liquid to a solid, where both of them are equally affected, but not very much. It doesn't mean there's zero effect, and it doesn't mean we can't get a pressure effect on melting, but on gases it's much higher. So that's a little foreshadowing, because we need to think about what entropy is. We'll probably do that next time. But what I wanted to do first was a different thing, or what I wanted to do this time was a different thing. So the other theme, the theme that I really wanted to finish on today, was about what thermodynamics is about, and what it's really telling us, and what happens over a very long time to things. So if we imagine this box contains water, like this, water. So we put lines in it to show that it's liquid water, and we put a block of ice in there. And then we arrange for it to be at 0 degrees centigrade. So I've put in a pentagon of ice in there, and we arrange for it to be at 0 degrees centigrade, and then we leave it for a really, really long time. Why is that important? Well, the importance is that thermodynamics tells us what would happen if we waited for infinity time. So if we take a thermodynamics and we calculate what should happen to this pen, for example, it should decompose, it should convert into carbon dioxide and water eventually. It will take a really long time. If we take a diamond, we would calculate thermodynamically that it should turn into graphite, because graphite is a lower energy form of carbon than diamond is. But we never see diamonds turning into graphite because they do it very, very slowly. Likewise, if we take some uranium, the radioactive form, the 238. Whoa, I'm going to get this wrong. Oops, I checked. And obviously, unlike students, and with a possibility of 2, I got the wrong one. So it's uranium 235, a mass of 235, which is the more radioactive one, and it decays over time. So if we did a thermodynamic investigation of it, the thermodynamics would tell us that it should decay, but it doesn't tell us anything about how long it takes. The thermodynamics is just assuming that you wait infinity time, and then we get to some product. So let us do that with this ice. What the thermodynamics was telling us is that the Gibbs free energy is 0. We just had that. So if we set the temperature here to 0 and don't allow any heat to enter or leave, or we have 0 temperature outside as well, it makes no difference. So we say no energy is allowed to enter or leave this box. Then we can say the amount of ice will stay the same. Ish. So to a first approximation, the amount of ice will stay the same because when a water molecule escapes from the ice, is melted off the ice, it will have to break a bond. So locally it will get a little bit colder, the temperature will drop, and then that will motivate another one to stick on somewhere. But it's not necessarily the same one and not necessarily in the same space. So what would happen if we wait infinity time? We would expect this block of ice to crystallize better. We would expect the surface energy that was costing us money to start, that was what made our freezing point depress below 0, surface energy of this ice crystal to be minimized over time. So if we imagine it was lots of tiny crystals inside this solution, over time they would melt and others would freeze, and we would end up with one bigger crystal. Theoretically, we would end up with the most perfect possible crystal and water, because that is a lower energy state because we've got the least amount of surface. But obviously we're also fighting against the minimum surface area, which would be a sphere. So then we can get a lower energy state. If we get a lower energy state, it gives out some heat energy, and it's because we've used up some sides, and that will make more water and less ice, which is why I said not quite the same amount of ice. So that happens with ice and water. What happens with water and gas? So now I've got water and I've also got gas, and they're in equilibrium with each other, which is not all that hard to do in reality. So we've got water vapor, evaporated water, we've got liquid water, and we're below boiling point, so no explosive processes happen. But what happens if we wait forever? Well, what do we have here? We have exactly the same situation that we had with the bubble of water and the boiling, that we've got a curved interface, and that will be creating pressure inside the drop. So the pressure of the water here is different to the pressure of the water here, because the curvature is different. And in this little pool here that I cleverly drew on here with a flat surface, don't usually do that, but it has no pressure difference. It's got the same pressure inside as it does out here. And that pressure will won't try, that's a really bad way of saying it, but it's a tendency of a way to explain it, but it's not a very good explanation. The pressure will cause the water inside to have a lower boiling point or a higher vapor pressure. And so although we're at equilibrium, so there is water in this gas phase that's going to this drop, and water in the drop that's coming out, water is going into this drop and coming out, and water is going into the pool and coming out, the rates aren't quite the same. So the small drop will be evaporating slightly faster. The condensation will be pretty much the same. The next size drop will be not quite as fast. The bigger drop will be a bit slower, and the pool will be the slowest. So if we wait for a very long time, what will happen is these drops will evaporate and this one will get a little bit bigger because it will cannibalize the others. The total amount of water, liquid water, is staying the same because we're not allowing any heat transfer with the outside world. It's not very realistic, I know, but it's a good thought experiment. So if we then carry on, and this will fit in here, or we can squeeze it onto the top like that, then we will eventually transfer all of the water into this pond. To have a pond that's a little bit bigger and reduce the surface area of the water, which gives us some free energy back, and also it will also reduce the pressure difference between the water and the gas, which is an extra factor that we would normally ignore if we were going to say that the boiling point is 100 degrees. So we've got this extra factor that we have to worry about. If we want to see what happens to drops, they will tend to evaporate if they're small enough, which is why an evaporative cooler or one of those smoke machines to add water to the air makes very, very small drops and they evaporate quickly. It's not just that they have a high surface area, it's also the pressure difference inside. So that introduces us, or brings us very close to two other topics that we will want to think about. One of them is, what is entropy, and can we have a little better definition and think about it a little bit better? That was what came up earlier. And the other one is, what forces are holding the water together? Because we've seen some effects of surface tension, but we haven't really thought about where it comes from. We've just used a model, which is the engineering model, that just says, okay, we've got some stuff, then we've got an interface, and the interface has these properties, but we don't know why. That's okay. It's okay for doing calculations, it's okay for predicting things, but as I said earlier on in this topic, very often we have more than one model for the same thing, and I would like to introduce you to a way of explaining why there is surface tension, so we can then use that for other things. So we'll have that as another topic as well. What I'll probably do next time, however, is boil some liquid. I'm not entirely sure which, but I'll boil some liquid and I'll change the pressure. I probably won't increase the pressure because that is difficult and it becomes dangerous. So I'll reduce the pressure and we'll get something to boil at less than its normal boiling point. So either water, which usually boils at 100 degrees C at atmospheric pressure, or ethanol, which boils at 74-ish, 74 or 76, or methanol, which is lower, 60 something. That we can bring down to a low temperature. We can get them fairly low if we get a good vacuum. Then we can demonstrate that, we can measure it. If we get it cold enough, we can freeze some water on the outside of the flask with the evaporation. It's difficult to do with water because the water inside freezes and that stops it from evaporating as fast, but we can do it with not water. So we'll try that, and then we will come back to those other themes which are more thermodynamics-y. Then, until then.